not exciting though.
It's doubly recorded.
We're
Okay.
back.
So the next thing I want to talk about is something related to fields and stuff, but it's different. But we're going to do some things that are on test one right now, so it's not a complete waste of time. And this stuff, I think, is on your first lab. Did you hand in your first lab yet, or no?
You have the answers?
No. But one of the things we're doing is electric potential, which is on the first lab. All right, so the beginning of this is set up weird, but in the end, it makes sense. So what you got to do is just wait until I'm done explaining everything and then put it all together, because it may be a little bit hard to follow as we go, but in the end, it will make sense. Okay, so what we're going to do is talk about these two new things called electric potential and electric potential energy, which are related to one another. But before we do that, we're going to go back to something that we should know from Physics 1, which is potential energy due to gravity. So we have to go back and think about how we did potential energy due to gravity. So this has nothing to do with electric force just yet, but it will be. So you actually, you have gravity, which goes down, right? So the weight force goes down. Suppose you're trying to lift something up, right? So you're going from here to here. So your displacement is positive in the sense that you're going up, right? Your final y value is bigger than your initial y value. Now, does anyone remember where we get the equation for potential energy for gravity from? It is, yes, but where does that come from? It's due to the fact that the weight is a conservative force, and for conservative forces, we can figure out the work done by a conservative force and moving it in some direction. And the change in potential energy is the negative of that work done, if you remember where that came from in Physics 1. So if you move this thing up, you can calculate the work done by the weight force. Remember, work is F times the amount of the displacement. In this case, the force is the weight. But the weight times the amount of the displacement times the cosine of the angle between the displacement and the force, in this case. The orange arrow and the blue arrow, right? So it's the angle between the orange arrow and the blue one. 180, the cosine of 180 is minus 1. So the work done by the weight force when you move something up is minus mg delta y. And delta y here is positive because the yf is bigger than the yi, delta y is positive. So you get a negative work, is what I'm trying to say. But that's not important. What's important is the change of change in potential energy, which is the negative of that. So instead of getting minus mg delta y, you take the negative of it, you get mg delta y, and that's where the change of potential energy comes from. That's where the equation for potential energy by itself comes from. But the thing I want to focus on for this, and so we can use it for the case of electric force, is what is the change in electric potential energy? How much does it go up or down by? That's what we want to focus on. So when you move something up, the delta y is positive, right? So you get a positive answer for mg delta y, which means that the potential energy due to gravity increases, right? If you raise something, you increase the potential energy of it. Now, from a conceptual point of view, does anyone know? So it's not math, but it's kind of hard. I don't know if I ever went over into Physics 1, but can anyone maybe guess at why moving something upward would increase its potential energy? Purely from a concept of...
Because it has more flight, it has more distance to travel, and we have more distance to travel, have more acceleration, and therefore...
Yeah, so basically the idea is, that's more or less, okay? But the basic idea is that it's going in the direction that it doesn't want to go. I mean, if you drop something, which way does it go? Does it go up or down?
Yeah.
Down, of course. So when you lift something up, you're building up its potential energy, right? And when you release it, more of it goes into kinetic energy, right? The higher it is. So the basic, what I'm trying to say is, if you move something in the direction that it doesn't want to go, the potential energy increases, and you get a positive delta EP. If something goes in the direction that it wants to go, in this case down, then you get a negative change in electric potential energy, meaning that the potential energy decreases, right, as it goes down. All right, does that make sense? So then we can apply this to electric force. So in this case here, all right, let me just say, a charge in a uniform field, which produces a constant electric force, right? So in this case here, we have a parallel plate capacitor that's where the positive sheet is here and the negative sheet is here. So the electric field just goes straight down. And you put a positive charge into this field. So this is what you should know for physics. On test 1 is what I meant to say. I was going to say physics 1, but I meant test 1. So if you put a charge in an electric field, you should know how the electric force is created by the field. So if you put a positive charge in the field, which way does the electric force go? With the field, right? If you put a negative charge, it goes opposite of the field, right? Anyhow, so if the electric field is down, the electric force acting on this thing is down, right? But it's a constant force, just like the weight's a constant force. So this picture looks like this. If you take this charge and you move it straight up with the electric force going down, does that look any different than this sketch here? I mean, schematically. No. I mean, obviously there's a different force. But besides that, it's the same picture, right? So without knowing anything about what electric potential energy is or anything, can anyone guess? I mean, it's on the next slide, but can anyone guess what the change in this new thing called electric potential energy is? If the change in potential energy to gravity is, where is it? It's mg delta y, right? So what would it be for electric force for the same situation? Instead of W, you have Fe, the electric force. What do you think it would be for the electric force? Fe delta y, right? Fe delta y, because it's electric force times delta y. But Fe is Q times E, right? This is something else you should know for test 1, right? If you put a charge in an electric field, electric force on it is Q times E, right? Absolute value Q times E. So the point is, for this particular case, if you move the charge up, the electric potential energy is QE times how far you move it up, which I say is D, right? How far you move it towards one plate or towards the other plate, which I say is D, QED. But the problem with the electric force is it's much more complicated than weight. See, weight only goes one way. And you basically can just move up or down, right? But electric field can be any way. It doesn't have to be it doesn't have to be vertically downward. I can rotate the plate so it's horizontal. I can rotate the plate so it's at some weird angle, right? Not only that, for weight, you only have a mass. The mass is always positive. For this case here, you have a charge, and charges can be positive and negative. So it gets way more complicated. There's all these different permutations of positive and negative charges and electric fields going in different directions. So the gist is this. It's the change in electric potential energy is QED something, plus or minus QED, right? So the question is, when is it plus QED? When is it minus QED, right? So the idea is what you got from the weight force. So when is it positive? So when, in general, is the potential energy, the change in it, I should say, positive?
When it goes down to up.
When it's going in the direction that it doesn't want to go. So when you push a positive charge towards a positive sheet, your change in potential energy is positive, QED.
It's kind of like elastic energy in a way, like the closer they are, the harder they'll repel from each other. They'll repel.
That's the same situation, right? So when you have a spring and you press it and it doesn't want to go that way, so that, right. And if you, if you push a negative or a positive charge towards the same sign, right? It's positive QED. If you push it in the direction where it wants to go, to the opposite sign, then it's minus QED, right?
Yeah.
That's it. That's the general idea, right?
So this is potential electric energy, like that thing?
Yeah, this is the energy created by the electric force, right? It's the same sort of thing as created by a spring or created by gravity, right? All right, so does that make sense so far? There's another way to view it, but we'll get to there, right? Now, this D, right, is going either towards the sheet or away from the sheet, directly towards the sheet or away from the sheet, how I have it defined there, right? In other words, they either go this way or that way, right? But maybe you don't go straight towards the sheet or straight away from the sheet. Maybe you go like this, right? At some angle. So for that case, what you need to do, so the general way to look at it is whether you're going against the field or with the field, right? See, if you're going against the field, you're going towards a positive charge. If you're going with the field, you're going towards a negative charge, because that's the way fields are defined, right? Anyway, the point is, suppose the field's like this, and you're going like this. So this is like, you're going like this, right, in this picture here. Instead of going straight, you're going like this. So the question is, how would you do it for that case? All right, so for that case, you just got to draw a triangle and figure out how far you go, either straight towards the plate or away from the plate, right? That's the thing that we consider. So you draw a triangle, right? This is how far you go. That always forms a right triangle. And this is how far you go, either towards the sheet or away from the sheet. That would be the D in general. And the D would be, just by trigonometry, r cosine theta, right? That's how you figure out how far you go towards the sheet or away from the sheet, right? That's how you would modify it if you're not going directly towards the sheet or away from the sheet. All right. All right, so everyone have that so far? All right, so the thing with electric potential energy is it depends on three things. What does it depend on? It's plus or minus QED. So what are the three things it depends on? Q, E, and D. Right? It's not that hard. It depends on the charge. So if you put different charges, you get different. It's a minor. It seems simple, but it's not. If you you got to think about it. If you put different charges in here, you get different answers, right? It depends on the field. It depends on how you move in the field, right? Which way you're going with the field. Which way you're going towards the positive sheet, or you're going towards the negative sheet. This other thing called, this is what I just said, the conceptual understanding. I went over all that. The next thing I'm going to talk about is electric potential. Now, electric potential is kind of like electric force and electric field. Remember electric force, you need two charges at least, but for electric field, you don't need two charges. You only need one charge. So for electric potential energy, you need three things, Q, E, and D. For electric potential, you don't need the charge. It's something that only describes basically the field and how you move in the field. So what electric potential is basically voltage, more or less. And what you can do is you can get how the change of voltage or electric potential is defined is if you're moving a charge in a field, in this case a uniform field, this only applies to uniform field, if you take the change in electric potential energy and divide by the charge that you're moving around in there, that gives you the change of electric potential. So they're almost the same terminology. One's potential energy, but they're two different things. That's given by delta V, right? So the delta EP is what? Plus or minus QED. So if you divide by the charge, what do you get? You get plus or minus ED, right? It's either plus ED or minus ED. So the question is, when is it plus or minus ED? It's actually kind of easy to understand. I'll get back to the units in a second here. But basically, when you go towards a positive charge, any positive charge, in the case of a uniform field, you're going towards a positive sheet or whatever, the potential increases, so your delta V is positive. So it's positive ED if you get closer to a positive sheet. The other way to think about it, is, so you can either think of it as going towards a positive sheet or going against the field, right? Because the field always goes from away from positive towards negative. So if you're going in this direction, you're going against the field, right? So against the field or towards a positive sheet is plus ED. If you go with the field or towards a negative sheet, it's minus ED, and that's it. That's how you understand what delta V is. Now the delta V is just how much the potential changes, which is measured in volts. It doesn't tell you actually what the voltage is. At a certain point, it just tells you how much it changes from one point to the other. So an example of this is if, and we'll talk about this in more detail when we talk about capacitors by themselves as a whole topic, just analyzing how capacitors work in more detail. But the basic idea is you take two sheets, you hook a battery up to it, that forms a capacitor. It's pretty simple. So if you take a 10-volt battery, hook it up to a capacitor, for instance, one side will be 10 volts, the other side will be 0 volts. Now, what you find when you find delta V is plus or minus ED, right? Suppose you go this far, you know the field, and you go this far. What it'll tell you is that delta V is plus 2 volts, right? That's what it tells you. It changes by 2 volts. So you go from 0 to 2 volts. Then if you do the same thing again, the E and the D don't change, right? Because it's the same field, you go the same distance. It's the same delta V, which means if this is 2 volts, then this is 2 volts. So you go from 2 volts to 4 volts, right? And then you keep on going, and you go to 6 volts, and then to 8 volts, and then to 10 volts. And that's how you get the individual voltages. What you're figuring out with this equation, delta V plus or minus ED, is how much it changes by, right? So the next question would be if you go horizontally, right? Suppose you start here and then wind up over here, but you go horizontally. What would the delta V be? It's 0, because you're not getting closer or further to any sheet. Another way to look at it is that you're going perpendicular to the field, right? So these are called what, do you think? They're in your lab. Right, equipotential line, meaning everywhere on that line, it's the same potential. Doesn't mean it's 0, by the way. It would be 8 volts and it would be 8 volts, but the difference of those two things is 0 volts, right? 8 volts minus 8 volts, which is 0 volts. But it's still 8 volts, right? The potential on each line, right? It's not 0 necessarily. Okay, so does that make sense? And the last thing I want to do, and then you can take your break, by the way, is you might be saying, well, why do we care about this? Well, one thing we care about later on is voltages. We need to understand how that works, or basically electric potential. And the reason why we care about voltage or potential is because we can use it to figure out electric potential energy. And if you can calculate electric potential energy or the change of electric potential energy, then you can do conservation of energy with the electric force, right? So remember conservation of energy from physics 1? You have this thing called total mechanical energy, which was kinetic energy and energy due to gravity and energy due to a spring if you had a spring. Well, the electric force is just another conservative force, so that goes into the total mechanical energy. So in physics 1, you had this, you had this, you had this, but now you have this new thing in there from physics 2, electric potential energy, if there's electric force. And then conservation of energy doesn't change. The change of energy is equal to the work done by non-conservative forces, which is like friction or basically anything besides, well, weight, spring. Now you have the electric force, right? Anything besides those 3 forces. And you just plug it into conservation of energy, and that allows you another way to calculate how charges move, basically, right? You can figure out how fast they're going. Things related to energies, right? So it's another way to calculate things. And in fact, when we have point charges, which we'll talk about on Thursday, in the context of this stuff, the only way you can figure out how point charges move around other point charges is by doing conservation of energy, because it requires calculus otherwise. So the only way you can do it in this class is with conservation of energy. Okay, so take a break. When you come back, we're going to do this like crazy long example with all this stuff in there. So, like I said, now what we're going to do is do this long example. All right, so we're actually going to do it in sort of opposite order as I went through it in the PowerPoint, but it's actually the better way of thinking about problems like this. So we'll see how to do it. Anyhow, you have a parallel plate capacitor. So this you might have to know for test 1. Parallel plate capacitors. Okay, so so I have it set up this way in my notes, although there's a much better way of sort of describing what's going on here, but for some reason it's set up in a certain way. I just like keeping in that way in case something goes weird. Anyhow, so you have a parallel plate capacitor. This is a parallel plate capacitor, so I'm just going to make it black. And this sheet, because you have to be told what sheet is what. So this is the negative sheet, and this is the positive sheet. And so we're going to have two charts. It's two different problems, but we're going to see how two different point charges are moved around in this capacitor. So one of them is going to be positive, and this is the part that's may be unnecessarily complicated, but it doesn't really matter in the end if you understand what's going on. So it starts at point 1, right? So wherever this thing originally is point 1. And then point 2 is it moving up like this. So in other words, if it goes from 1 to 2, it goes up some amount. But instead of saying it goes from 1 to 2, I can just say it goes up something. But for some reason, I wanted to label it like this. It goes from 1 to 2, 1 to 3, so on and so forth. So when it goes from 1 to 3, it goes down by some amount, which I'll tell you in a minute. And when it goes from 1 to 4, I don't know why this always does this in this class a lot. It goes to left some amount. So this, straight to the left. So point 4 is to the left of point 1. And they're all the same distance, right? It goes up some distance, it goes down some distance, it goes to the right some distance, the left is what I had to say, some distance, and they're all the distances are the same. It's just 0.1 meters up, down, left. And then it's the same thing. It's two different sort of problems as you'll see, but we're also going to see what a negative charge does in the same capacitor. So, in other words, a negative charge going up, 0.1 meters down, 0.1 meters to the left, 0.1 meters, right? Anyhow, that's the setup. So the first part A, could be something on test 1. So for instance, the question is, what is the amount and direction of the electric field produced by the capacitor? Because we need to figure this out to answer anything else related to the problem, but this is on test 1, right? The electric field of a capacitor. So does anyone know how to find the electric field of a capacitor? It's the surface charge density, the charge per unit area, divided by epsilon 0, right? So it's an epsilon. It's not a charge. It looks like a charge, but it's an epsilon. So you have to convert the charge per unit area, which is this thing here, 2 microcoulombs per meter squared, meaning every meter squared there's 2 microcoulombs of charge in that in the sheet of the capacitor. And then you divide by epsilon 0, which is 8.85 times 10 to the minus 12. Coulombs per Newton meter squared. Anyhow, this equation and the epsilon 0 on your equation sheet, all the constants are at the bottom of the equation sheet. So you just plug this into your calculator and you get some number, and it's a big number. It's 2.26 times 10 to the 5th newtons per coulomb. So that's how much the field is, just using the equation for a capacitor. Why does it do that? I know why it's doing it, but I don't want to fix it. I just figured it out. Okay, so that's the amount of the field, but you also have to find the direction of the field, or at least sketch the direction of the field. So let's do that.
Actually, girls, I have a question.
Uh-huh.
If you look at the units, I would think,
Uh-huh.
like, it would just be units, rather than things over coulombs.
So the meters squared, coulomb squared per, yeah, that's right, I forgot a coulomb squared. Coulomb squared per Newton meter squared.
Okay.
That is newtons per coulomb, yes. Okay, so what does the electric field look like for this case? Which one, this two?
Yeah, the 2 on top. Oh, I didn't see that.
That's okay.
Thank you.
Yep. So in general, how does electric field, what does it look like?
It goes from negative to positive.
Right. So for this case here, you can just draw a couple lines. You know, if you want to draw more than a couple, it's fine. It doesn't matter. But I'm just going to draw two. So electric field looks like that, right? From negative to positive. So, you know, maybe it'd be the negative y direction for this case. But the point is we don't need to specify it. We just need to know what it looks like. Just sketch it. Okay, so does that make sense? Right? How do you find electric field? Because that could be on test 1. All right, next part, which is the new stuff, is for either charge, and I'll explain why it's, you know, either charge. What's the change in electric potential, which is not electric potential energy? So the first thing I talked about, by the way, before the break, in the new PowerPoint, was electric potential energy. I'm not asking about electric potential energy. I'm asking for electric potential as the charge moves from 1 to 2. Okay, the reason why it's either charge is because this thing, the change in electric potential, does not depend on the charge, right? It only depends on the field and how you move in the field, which way you're moving and how far you move. So, from 1 to 2, does anyone remember before the break how it goes for electric potential? So from 1 to 2, which way are you going? Almost. Are you going towards the negative sheet or the positive sheet?
Well, if it's a positive.
Yes.
Right, with the negative, yeah.
Yes. So, or the other way to look at it is you're going against the field, right? Either way. Now, the question is, if you're going against the field or towards the negative sheet, does anyone remember how it works for the change in potential? Yes. It's minus ED, right? Because you're going towards the negative sheet or against the field. What am I doing here? With the field. You're going to flip these around, right? My bad. Yeah. Yeah. Yeah, I just, when I was saying that, I'm like, that doesn't make any sense. So you go like this. I'll explain it one more time. You go towards the negative sheet, right? Yeah, that's how it looks, right? From positive to negative. Okay, so once again, if you go towards the negative sheet, it's minus ED, or with the field is minus ED. That's the proper one.
This is charge 1.
Either charge.
But if the charge is negative, why would we go towards negative sheet?
We're not talking about the charges. We're talking about
The
either,
sheets.
yeah, the fields, right? So it's minus ED, either going with the field or towards the negative, sorry, delta V. I'm messing up everything today. All right, delta V is minus ED. That's what I want to write in general, right? So we have the E, because we found it in part A. So either you're given the E, or you find the E like we did in part A, and you multiply it by a negative sign because it's minus ED, and then you multiply by D, how far you go. So we're going 0.1 meters towards the negative sheet or against the field, and that'll give you the change of potential. So it's negative 2, so it's the same thing because you're just multiplying by 0.1, except it's times 10 to the 4th, right? Because if you multiply by 0.1, that just reduces this by 1, and it's not newtons per coulomb. Does anyone know what the units are? Yeah, Newton meters per coulomb. But does anyone know what volts? It's a volt, right? So it's negative 2.26 volts. So basically, if you go 0.1 meters towards the negative sheet, the voltage goes down by 2.26 times 10 to the 4th volts. All right, does that make sense? Okay, so the next question is pretty similar to this one, but obviously different. So the only difference is we're going from 1 to 3. So from the answer for B, or from 1 to 2, you could probably guess what the answer is for 1 to 3, but if it's a totally separate problem, When you're going from 1 to 3, you're going towards where? The positive sheet. If you're going towards a positive sheet, the delta V is positive. It increases. The other way to think about it is if you're going against the field, that also increases the potential. So instead of it being minus ED, what do you think it is? It's just positive ED. And if the E is the same, which it is, from a capacitor, it doesn't matter where you are in the capacitor, it's the same field. You're going the same distance, the same answer, except it's positive, right? So if you go 0.1 meters in the towards the positive plate against the field, the potential increases by 2.26 times 10 to the fourth volts, right? I mean, these questions aren't super hard, and the equation's pretty easy, but you gotta, get your signs right, because that's a gigantic problem on a quiz or a test or the homework, right? You gotta make sure all the signs are correct. Now, the last part with potential is, suppose you go from 1 to 4, which is basically parallel to the plate or to the left. So what would your delta V for that be if you go from 1 to 4? It'd be 0, because you're not going closer or further away from any sheet, so your delta V is 0. The other way to think about it is you're going perpendicular to the field, right? Whenever you're going perpendicular to the field, the delta V is 0, right? So this is just 0. Because the D is basically 0, right? You're not going towards or away from any sheet. All right, so does that make sense? All right, so that's all the questions you can ask for delta V. Now we're going to get to the change in electric potential energy. Now the change in electric potential energy depends on the charge, so we have to pick charges for this one. So this is for I think I'm doing the positive charge first, so that doesn't really matter. I can do the in any order. Yeah, but for the positive charge, all right, so here's energy, right? So we're talking about the energy, not electric potential. As it moves from 1 to 2. So this answer does depend on the charge. Different charges give you different answers for this one. So the way we did it in the notes is we used the electric potential to figure out delta V, the equation for it. Here we're going to do it backwards. In other words, the equation for delta V was you take the change of electric potential energy, whatever that was, and you divide it by the charge that you're moving. That gave you the equation for delta V, which is plus or minus ED. Here we're doing it backwards. In other words, and this is the way you typically do it, by the way. In other words, if you know the change in potential as a charge moves from one point to another, you just multiply the charge by your change in potential, and that gives you your delta EP. There's a hugely important thing to note about this, though. Normally, we write things with absolute values all over the place. There's no absolute values here. So the charge can be positive or negative, and you just saw delta V can be positive or negative. So you got to be a little bit careful with your signs because there's no absolute values here, right? Each thing can be positive or negative. But nonetheless, if you're careful with your signs, it's pretty straightforward. So for this case here, all you do is you take your charge that you're moving. In this case, it's the positive charge, which was, I think, 3 microcoulombs. But it's positive. Is it 3? It is 3, right? And you multiply it times the change in V from 1 to 2, which we found in part B, I think, right? So the change of V from 1 to 2, which is part B, was this number here, right? So this is negative, but the charge is positive. So what is the sign for your delta EPE in the end?
Negative.
Right. So you get a negative answer for your delta EPE because one's positive, one's negative, and you get negative 6.78. All right, what's the units? I didn't really go over the units, but
So it's going to be newtons times meter. No, newtons as meters.
yeah, that's true. But like in terms of like anytime you see an energy, right? Yeah, it's joules, right? Yeah. So it's negative 6.78 times 10 to the minus 2 joules. So now what I try to point out is that you can use math to get the answer, which is fine. But the problem with the math is there's a lot of chances to get things wrong. You can get the sign wrong here, you can get the sign wrong here. On a test or quiz, if you get the sign wrong, it's wrong. So you go to check to make sure it makes sense. Your sign makes sense from a sort of conceptual point of view. So when is the case if you're calculating the change in electric potential energy and it's negative, or in other words, it's decreasing, not increasing? What does that mean in general? Does anyone remember?
The potential energy is going down. Like, in other words, it's going closer to where it's like you would naturally want to go.
Right. So let's see if that's the case for 1 and 2. You have a positive charge going toward the negative sheet.
Right.
So that's the direction that it wants to go. So you should get a negative answer. So you should check it all the time, because it's easy to get one of these signs wrong, and then it's wrong on a multiple choice test, or it's wrong on the quiz, or a homework, right? So you want to double check to make sure your sign's right at least, right? All right, so it's right? It makes sense. Everything makes sense. All right, so then, of course, we're going to do like the same kind of problem for the other sort of permutations of all these things. So we're going to do the positive charge from 1 to 3. But that's pretty straightforward, hopefully, if you understand 1 to 2. So from 1 to 3, it's the same equation, right? Everything's the same.
It's positive.
The only difference is the delta V is different, right? From 1 to 3, it's not negative 2.26, it's positive 2.26 times 10 to the 4th. So that's the only difference here, right? So this number is the same thing, but positive. Once again, you're just using the math, and there's a lot of signs there, right? So you want to check again. Does that make sense? Does a positive sign make sense? So what does it mean if you have a delta EP that's positive? I mean, conceptually speaking, it's going in the direction that it doesn't want to go. So once again,
So it's going towards it's the same sign.
right, the positive charge is going towards the positive charge, doesn't want to go towards the positive charge, so therefore it should be positive.
So question.
Yeah.
Can we technically say the charges are in equilibrium because the same amount of same amount of work, right? Work we call it, needed to push it towards the negative sheet is the same amount of work needed to push it towards the positive sheet, except one's positive, one's negative.
Mm-hmm.
So in a way, like because they're equal, what is they consider equilibrium or
No.
not? No.
Yeah. I mean, if you have two different fields, one going up and one going down, and the same, then that would be the case, but not for this case. Okay, so the last part is easy, probably the easiest one for charge. Yeah. So, yeah, for the positive charge, all right, so what is this part? G? We're in G? E, F, G, right, yeah, okay. So for 1 to 4, okay, so this is easy, right? What's the potential as it moves from 1 to 4? The change in potential.
0.
So what's your change in electric potential energy?
0.
0. So whenever a charge is moving along an exponential line, there's no change in electric potential energy, right?
So it's equal potential, no?
Yeah, that's what that would be, right? If the delta V is 0, it's equipotential. All right, so does that make sense? All right, so then we're going to do the same thing for the negative charge. This is H. All right, so for the negative charge, what's the change in electric potential energy from 1 to 2? So the delta V doesn't matter for positive or negative charge, but the delta EP does, right? Because that depends on Q. There's a Q in there. So this was -4, right? So you don't put the absolute value, right? That's a huge difference from what we did before. Now the delta V from 1 to 2 is negative, right, from part B, and the charge is negative. So what do you get as your sign?
It's be positive because for 1 to 4, it's going towards the positive, whereas the charge is negative, so it's going towards where it wants to go.
Yeah, in this case here, it's positive, right? So it's going towards, if you get a positive answer.
It makes that it's going towards where it doesn't want to go. Therefore, it's going to be positive.
Yeah, so this case here, it should be going in the direction it doesn't want to go. And if you look, it's going in the direction it doesn't want to go, right? A negative charge going towards a negative sheet should be positive. So while we're here, right? If you go down, what should the sign be? You have a negative charge going towards a positive sheet,
It's gonna be negative.
right? And then,
It's gonna be negative, right?
yeah, and then if it's going horizontal,
If it's going where it wants, it's gonna be negative because
Right.
there's less potential from there.
So if you ask the same question, right, that we just asked, but you ask from 1 to 3, we should get a negative answer, right? All right, so this is, see, I told you this has a lot of parts, from 1 to 3.
Think about magnets. The magnets don't want to connect.
That's
They
all I
don't want to
think, yeah.
connect. It's exactly
Yeah,
the same.
we'll talk of it. Okay, yeah. Okay, so that's positive, right? Because from 1 to 3, the delta V was positive. And then just by math, you get a negative answer. But then, of course, we just went over it. It should be negative, right? Because you have a negative going towards a positive, right? So it should be negative. All right, so does that make sense?
Yeah.
And then the last one, which is the easiest one,
1 to 4, so also be 0.
yeah. So this is J, right? Oops. All right, so 1 to 4, same as it was a few parts ago. This is 0, so it doesn't matter. This is the only time the charge doesn't matter, obviously. If the delta V is 0, then you get the same answer, right, for either charge. So it's 0 joules, right? Okay, so that's how you figure out the delta EPE, delta V for uniform fields. We'll get to other cases on Thursday. But the next thing the reason why we're doing this is to use conservation of energy, which we'll do after this part. Sorry, I forgot. I always forget. There's one extra part in between this and conservation of energy. So this becomes relevant when we focus more on capacitors by themselves. So we're going to spend a whole class or two just talking about capacitors and how they behave. So we sometimes need to do something like this when we talk about capacitors. Okay, so what I mean by this, just so you have a sketch, I'm just going to copy so on. Okay, this, right? So I have this capacitor, and we have this field produced by the capacitor, which we know from part A. So the question is, right, if you go from the negative sheet to the positive sheet, all the way across the capacitor, how much does the voltage change when you do that? This is also known as finding the voltage across the capacitor. That means how much does the voltage change from one sheet to the other sheet, right? So this is, I'm going to call it D prime because we use D as the other variable for the first few parts. So this D, this is obviously 0.5 meters. So it's not a trick question. It's basically what we did before, right? So if you go from the negative sheet to the positive sheet, what's your delta V? Is it plus ED or is it minus ED? If you go towards the positive sheet. Positive. So your delta V would be plus E D prime, right? Where D prime is the new distance that you go across. The field is the same as it was for part A. So it's plus and then you would multiply this by 0.5. Or you could do proportions, because when you use 0.1, 0.5 is 5 times bigger than 0.1. So the field would be 5 times greater. I mean, sorry, the delta V would be 5 times greater. The field is the same. It doesn't change. So if you multiply the first delta V by 5 that we did in part B, I think, you'd also get the same answer. So it'd be plus 1.13 times 10 to the 5th volts. So what we're saying is, if you go from the negative plate to the positive plate, the voltage increases by 1.13 times 10 to the fifth volts. And we commonly refer to that as the voltage across a capacitor. It's 1.13 times 10 to the fifth volts for this case. Now, typically what we do when we talk about a capacitor in this sense is we normally say that the negative sheet is at 0 volts. This is typically what we do. And we'll get into more of this when we talk about capacitors by themselves. But usually we say this is 0 volts, right? If that's 0 volts, then all the way to the other side goes up by 1.13 times 10 to the fifth volts. That means that the positive side is 1.13 times 10 to the fifth volts, right? Because you start at 0, and it gets bigger and bigger and bigger, and finally when you're at this side, it's 1.13 times 10 to the fifth volts, right? So that's the voltage across the capacitor, which we'll see later on, right? Now, there's another half part I'm going to do because I started it in the other class, then I ran out of time. And we'll finish it on Thursday. And that is, for the positive point charge, this is the reason why we're doing this, or at least one of the reasons. What is its final velocity if it started from rest at point 1 and ended at point 2? It's not the best way to say it. So if it starts from rest at point 1, what's its final velocity at point 2 is what we're trying to say. So the mass of the charge is 0.05 grams, not kilograms. And we're going to ignore the weight force for this case. So you might say, well, there's a weight force. Yeah, there is a weight force, so it's not particularly realistic. However, in some cases it is, because the electric force is a lot bigger than the weight force, and the weight force sometimes doesn't even matter. For this case, it wouldn't matter much because the mass is so small, the weight force would be so small, and the electric force would be a lot bigger. All right, so I already kind of went over this in the PowerPoint, but let me just go over it one more time. So in general, the total energy from everything could be due to the potential energy due to gravity, which is just PE. The potential energy due to a spring, which is PES. The kinetic energy. And now, electric potential energy. This is the new thing. Of course, if we ignore gravity, then this is 0 because there's no gravity. And there's no springs here, so that's 0. So it's just the kinetic energy plus the potential energy in general, right, for us, right? So the initial energy would be this, right? This is how much energy it has at point 1. It would just be whatever kinetic energy it has, which we can simplify, but I'm just going to leave it like this for now. So whatever kinetic energy it has at point 1, or the initial point, plus whatever electric potential energy it has at point 1, which is the initial point. Now the problem is we don't know what this is. We know how much it changes by, which is what I'm getting to. The final energy is something similar. It's the same thing. It's that you're just changing this to the final points, right? In other words, how fast is it going? Or sorry, what's the kinetic energy at point 2, right? That's the final point. What's the electric potential energy at point 2? But once again, we do not know these two things. We know how much it changes by, right? So we have to put this into conservation of energy, which I kind of did on the PowerPoint, but let me just show you one more time in slow motion where this comes from. So how you put all this together is that the change of energy is equal to the non-conservative work done, which is basically work done by everything but the electric force, gravity, and the spring force, right? Anyhow, this, by definition, is EF minus EI, right? Because that's whatever the change of something is, right? It's always the final thing minus the initial thing. Now, the final thing is this thing, right? This is the final final energy. This is the initial energy for this particular case, right? This is in general for this case. We're going to simplify it on Thursday. So when you sort of distribute this negative sign through, this becomes KEF minus KEI. This becomes EPF minus EPEI, right? So what you get is this, which is delta KE plus so this is, yeah, we're going to use it a slightly different way on Thursday, but it's close enough. So that's what we know. We know the delta EP, that's what we found. And that's equal to WNC. So in this form, we can use what we already calculated to answer this question, right? Which is what we're going to answer the first thing on Thursday, right? Just finish this part and do another part. All right, so does that make sense? All right. So you guys can go, because that's how far I got in the other section.